You ever look at a physics problem and just get that feeling you're missing something obvious? Well, when it comes to vector components, the secret isn't about being a math genius. It's about having the right mental picture. And today, we are going to build that picture using a really simple, really powerful idea. So let's flip on the lights and see what kind of shadow this whole problem casts. So imagine this. You're pulling a little red wagon, right? You're pulling the handle, which is angled up and forward. But the wagon itself only moves forward flat along the ground. So here's the big question. How much of the energy you're putting in is actually moving the wagon, and how much is just kind of wasted, lifting the handle up? Believe it or not, that is a vector component problem.
And this visual just nails it, doesn't it? We've got two main things going on here. That orange arrow, the one pointing up and forward, that's your total force. We'll call it vector A. And the blue arrow, the one flat on the ground, that's vector B, the only direction the wagon can actually go. So our whole mission is to figure out how much of vector A is really pointing in the same direction as vector B.
Now to figure this out, we're going to use an amazing little trick. Before we even touch an equation, I just want you to think about one thing: casting a shadow.
This brings us to our big term for the day, the scalar component. Look, don't let the name scare you. All it means is the length of the shadow that your force vector, A, casts down onto the direction vector, B. That's it. It's just a single number, a scalar, that answers the question, how much?
Let's make this crystal clear. Picture a bright sun shining straight down, perfectly perpendicular to the ground. That light hits vector A, and vector A casts the shadow onto vector B. The length of that shadow, that is exactly what we're looking for. It's the part of your force that's actually doing the work.
Okay, awesome. Thinking about a shadow is a great way to visualize it. But how do we actually measure the shadow with math? Well, for that, we need to pull a special tool out of our toolbox, and it's called the dot product. As the legendary textbook Elements of Electromagnetics by Sadako tells us, the dot product is all about the angle between two vectors. See that word cosine in there? That's the secret sauce. If you remember your high school trig, cosine helps you find the length of the side adjacent to an angle in a right triangle. And in our shadow analogy, the shadow is the adjacent side. So the dot product is literally built for this job.
So here is the formula you need to burn into your brain. To find that scalar component of A along B, we take the dot product of our vector A with a very special version of vector B. See how it's written there with a little lowercase a? That little a is a huge deal.
That little a stands for something called a unit vector. A unit vector is basically a pure direction. It's got a length of exactly 1, no more, no less, and it points in the exact same direction as our original vector B. You make one by just taking any vector and dividing it by its own length. Simple as that.
Here's the best way to think about it. The unit vector is our perfect standardized ruler. It's exactly 1 unit long. So when we use the dot product to project our force vector onto this perfect little ruler, we get the true length of the shadow with no weird scaling or anything funky going on.
All right, enough theory. Let's get our hands dirty and actually measure a shadow with a real example. Okay, here's our setup. Our force, vector A, is 3, 4. That just means it goes 3 units to the right and 4 units up. The direction of motion, vector B, is 5, 0. That's just 5 units straight to the right. Our job? Find the shadow that A casts on B.
We're going to knock this out in 3 easy steps. First, we make our 1 unit long measuring stick, the unit vector. Second, we set up the dot product. And third, we just crunch the numbers. Let's go.
Step 1, we need our perfect ruler. Our vector B is 5, 0. I mean, you can just look at it and see its length is 5, right? So to get the unit vector, AB, we just divide the vector by its length. So 5, 0 divided by 5 gives us 1, 0. And there it is, our perfect 1 unit long ruler pointing straight to the right.
Now for the main event. We use our formula, A dotted with our new unit vector AB. So that's 3, 4, 1, 0. To do the dot product, you just multiply the first numbers together, multiply the second numbers together, and add the results. So that's 3 times 1 plus 4 times 0, which is just 3 plus 0.
And boom, there's our answer, 3. The length of the shadow is 3. So going back to our wagon, this means that your total force is actually contributing exactly 3 units of pure forward pulling power.
Now hang on, before we celebrate, I have to show you the #1 mistake people make with this stuff. It's a super common trap, but once you see it, I promise you'll never fall for it again.
So the question that always comes up is this. Why did we go through all that trouble to make a unit vector? Why not just dot A with the original vector B? I mean, it seems like it would be easier, right? Well, let's look at them side by side. On the left, you've got the right way, a dot AB. This uses our perfect one-unit ruler, and it gives you the true length of the shadow. On the right, the wrong way, a dot B. This does something totally different. It finds the shadow's length, which is 3, but then it multiplies that by the full length of B, which was 5. So you'd get an answer of 15. Your answer is now 5 times too big because your ruler was 5 units long.
It really is that simple. Forgetting to use the unit vector is exactly like trying to measure something with a broken ruler. If your ruler isn't 1 unit long, your measurement is going to be totally wrong. So, always use the unit vector. It's your perfect ruler.
Okay, let's lock this in. We covered a lot, but it all boils down to just a few key ideas. Let's do a lightning fast recap.
Here are the 3 things you absolutely have to remember. Number 1, the component of A along B is just its shadow. That's the mental picture. Number 2, you find the length of that shadow with the formula A dot AB. And number 3, the golden rule. Always use the unit vector as your perfect 1-unit ruler.
So we've totally nailed the scalar component. It's a number. It's a length. But you know, in physics and engineering, we don't just care about length. We care about direction, too. So what if you need to know the actual vector of that shadow? Not just its length, but which way it's pointing.
Well, that, my friend, is called the vector component. And the great news is you've already done all the heavy lifting. You just take the length you already found, in our case it was 3, and you multiply it by the unit vector, which is our pure direction pointer, 1, 0. So you get the vector 3, 0. You literally just take the length and give it a direction. Once you get the difference between the scalar component, the shadow's length, and the vector component, the shadow itself, you're well on your way to mastering vectors.